Hello friends, welcome to channel Teach Me Technically. What we are going to learn in this playlist is we are going to study computer architecture and the processor what we are going to study is MIPS. For all those who have not yet subscribed to our channel Teach Me Technically, subscribe it now. So now what we are going to do is we are going to discuss binary added subtractor. Here is the component of 4-bit added subtractor. What we actually want to do is we want a one single component which would not only add two numbers but also do subtraction on two numbers. So we want a single component that would do or perform this task. So here you can see something similar to the last slide. Here is the 4-bit binary adder which is shown right here. C0. This is full adder and second full adder, third and fourth full adder, which is actually shown in the last slide. So this is actually the binary adder, 4-bit binary adder. So you can see similar thing right here. So basically this thing is actually used to perform the binary addition. So now what we want to do is we want this component to also perform subtraction. So how we will use this component to perform subtraction? As you know that to perform subtraction, what we need to do is we need to take 2's complement of a number and then add that number in the given number. For example, I want to perform a minus b. Actually, what I will do is I will compute a 2's complement of b input and then I will add that 2's complement in the given input a, and then finally result would be a minus b. So something similar is going on in this binary adder subtractor. So to perform subtraction, what we do is we take four full adders and then give the same inputs like A0, A1, A2 and A3 as it is to these full adders. Now the task is we need to compute the 2's complement of the second input. So our second input is B. So B0, B1, B2 and B3, and we are going to compute 2's complement of it. So how to compute 2's complement? We actually need to perform two tasks. Number one is we want to flip the bits of the input B, and number two is we want to add 1 in the given number. So to add 1 in the given number is very simple. What we will do is we will simply input 1 from this carry C0. So basically what will happen is it will perform the simple addition of 1 in the given numbers. Now the basic task which is remaining is that how we will invert the bits of B and compute first complement of B. So we will compute first complement of B by using the XOR gates. And as you know the working of XOR gate, that if we give one input as 1, what XOR gate do is it simply flips the bit of the second input. So basically if B0 contains 0, so 0 goes here, and M contains 1 and M goes here in the XOR gate. So what will be the output of XOR gate will be the inverse of B0. So here we will get the output as 1. So if B0 is 0, output will be 1 in case M is 1, and if B0 is 1, the output will be 0 in case the other bit is 1. So in this way we will flip the bits of B0, B1, B2 and B3. When we need to perform addition between two numbers A and B, what we will do is we simply pass A right here and simply pass the value of M as 0. So in XOR gate when one bit is 0, the resultant bit is actually the bit which is the second bit. So whatever the value of B0, it will be simply passed over right here. So when the value of B0 will be simply passed right here, we will perform simple binary addition as we have seen in the last slide. So A0 come here, B0 simply comes right here, and A1 comes here and B1 simply comes right here. So the value of carry would be 0 as the value of M is 0. So this component will simply add A and B. But however, in the case when value of M is 1, this component will perform subtraction operation and compute A minus B. And simply how it performs subtraction is actually it will pass simply the value of A right here. And because the value of M is 1, and in case of XOR gate, it will simply compute the inverse of whatever the value is stored in B0. So it will produce the result of B complement right here. Now to compute 2's complement, what we need is we need first complement which has been computed right here by the XOR gate, and we need to add 1 in the given number. So to add 1, the wire of the carry input C0 has been attached to the M. So 1 would be added right here. So the inputs to these components would be A0, the complement of B0, and the carry input would be 1. So in this way, this component would compute A minus B. Whenever we perform addition or subtraction operation on our binary numbers, there is a risk of getting overflow. Overflow is actually that our number of bits in the output is actually greater than the number of bits given in the input. So let us take an example. We have two numbers -5 and -5, and we want to perform addition operation. So we have represented both the numbers in 2's complement, and when we perform addition operation, what we get is 10110. The number of bits we get in our output are 5, but the number of bits we gave in input were 4. So output bits are greater, so there is an overflow. Now there is a problem that how can we judge that either there is an overflow or not using hardware. It has been observed that overflow always occur whenever the value of C4 and C3 carry are different. So if the value of C3 and C4 are different, then overflow is definitely going to occur. So to find out that either overflow occurred or not, we have attached an XOR gate with our carry C3 and C4. And the output of this XOR gate tells us that either there is overflow or not. So if the output is 1, then there is an overflow, and if the output of this XOR gate is 0, then there is no overflow. As we know that XOR gate gives 0 whenever both the bits are same. So whenever both the values of C3 and C4 would be same, we would get no overflow, and whenever both the values of C3 and C4 are different, then we get an overflow. So now there is a question that what is the range of unsigned number and signed number? So here is the formula of range of unsigned number and signed number. For unsigned, there is a range from 0 to 2 raised power n whole minus 1. So for example, we have 8 bits, so the range would be from 0 to 255. Okay, and for signed number, there is a formula minus 2 raised power n minus 1 to 2 raised power n minus 1 whole minus 1. So basically, for 8 bits, its range would be minus 128 to 127 bits. So friends, if you understand the lecture, do comment in the comment box and let me know, because it motivates me to make more videos. So I hope you understand the lecture. Give this video a thumbs up. If you have any question, do comment and subscribe to our channel Teach Me Technically. Thanks for watching, friends.